This is the Electric Field 1 lab, and what I'm going over now, I will be also going over at the beginning of lab. But if you want to get a head start on your lab, you can watch this now. I will be providing your lab manual for you during our first lab meeting, and you can also find the lab manual on the M Drive. So if you're watching this because you are in the overflow room for the lab, you can watch this and get started on your lab rather than waiting for me to finish in the other room. And then I'll be going over the same thing in the overflow room when I finish in 7107. So on the first page of the lab, they give you the equation for the electric field, which we saw during lecture. We're going to use this equation and do calculations in today's lab. So we know the electrostatic constant is equal to 9 times 10 to the 9th newtons times meter squared per coulomb squared, where Q is the charge that is creating the field and the charge is measured in units of coulombs. R is the distance between the source charge and the point of interest. So if you look on the next page, we have two charges here. If we're looking at the sodium ion, that would be our source charge. If we're looking at the chlorine ion, that would be our source charge. And we're going to find the point of interest and calculate the electric field from each charge individually, and then add them together to get the net electric field using the superposition principle. So one of the most complicated parts of using this equation is figuring out what the different R's are. Now, what is not in this equation, but which is important to know, is what the vector R is. So let's say we have a charge Q here and our point of interest here. The vector R always goes from the charge to the point of interest. Okay, so that is the vector R. That does not appear in the equation that way. What we do have in the equation is R squared and R hat. So if I have this vector R, I can find the magnitude of the vector. So if this is the x direction, from here to here, that's the x component, Rx. This is the y component, Ry. And we can write the vector R as Rx in the I hat direction plus Ry in the j hat direction. And if your vector was going, let's say, this way instead, that would be a negative x component and a negative y component. Okay, so we have our vector here. I want the magnitude of the vector, so using the Pythagorean theorem, I can say that the magnitude of this vector is Rx squared plus Ry squared, and then take the square root. Okay, so that is now a scalar quantity and not a vector quantity. And one thing we have in our equation here is R squared, so that is the length squared, or the hypotenuse of our right triangle here squared. So R squared is actually a shorthand form of the magnitude of the vector squared. So that's what R squared means. It's this length squared. That length is the magnitude of the vector. But we're not going to write it that way. We're going to write it like this. Okay, so if I take the magnitude of the vector and square it, that would just be Rx squared plus Ry squared in 2 dimensions. And in one of the problems in this lab, we're going to have a 3-dimensional problem, so you'd just tack on a plus Rz squared. Okay, so that gives us the R squared there. Now I also need the unit vector. The unit vector points in the same direction as the vector R, but has a length of 1. So to make a unit vector, I take my vector r, but since my unit vector needs to have a length of 1, I divide by the magnitude. My vector r is rxi hat plus ryj hat. So this is rxi hat plus ryj hat. Then divide by the magnitude. This is the magnitude, so that's rx squared plus ry squared. And then take the square root, and that's again in 2 dimensions. So we have r squared, which goes in the denominator, and r hat, which goes in the numerator. However, if we're working in 2 dimensions, rather than going through this each time, we can just rewrite the equation that we have here. So in 2 dimensions, this equation becomes k times q divided by r squared, and r squared is rx squared plus ry squared, times r hat. R hat is rxi hat plus ryj hat, rxi hat plus ryj hat, divided by the magnitude because it has to be a unit vector, which is the square root of rx squared plus ry squared. Okay, and then look in the denominator. We have rx squared plus ry squared, and we also have a square root of rx squared plus ry squared. So if we multiply those, then we add the powers, and our new denominator becomes rx squared plus ry squared to the 3/2. So that's rx squared plus ry squared to the first power plus rx squared plus ry squared to the 1/2 power from the square root, and you add 1/2 and 1, which are the exponents, and you get 3/2 for your new exponent. Okay, and then the numerator is kq, and I have rxi hat plus ryj hat. Okay, so that is the 2-dimensional equation for the electric field. If it was in 3 dimensions, you would have a plus rzk hat in the numerator, and in parentheses in the denominator, you would have a plus rz squared. You can use this in 1 dimension by taking away the ry component, but it doesn't always make a lot of sense to do it that way. So if we were to do it in 2 dimensions, taking away the y component, or just setting ry equal to 0, would give us the electric field is equal to kq times rx in the I hat direction, and then we have rx squared plus ry, which we're going to say is 0 squared, so it's just rx squared to the 3/2. But if you have rx squared to the 3/2, that is just rx to the 3rd, but then we have rx divided by rx to the 3rd. That would become kq I hat divided by rx squared, which in 2 dimensions is what we started off with here, except r is now just the x component, and instead of r hat we have I hat. So it doesn't really make a whole lot of sense to write that. For 1 dimension, we would just use this formula instead. And in 2 dimensions, we have this. In 3 dimensions, you would have to add a plus rz in the numerator, a plus rzk hat in the numerator, and you'd have to add the plus rz squared in the denominator. Okay, so you can go ahead and use this formula in the lab, except for the last problem where it's in 3 dimensions. And this is where it all comes from. And if you can understand this, you should be in good shape for what comes up next. Okay, so I am going to do the next page for you as an example problem. Okay, so I'll be doing this in lab and also on the video here. So for this first page, all you have to do is copy down what I'm writing now, and you'll be good. for the first problem on the lab, and then you should be able to do the rest of it on your own. I do want to make one point on the next page though, which I'll do in just a minute. Okay, so a sodium ion and a chlorine ion are separated by a distance of 2.82 times 10 to the negative 10th meters. Find the electric field at 2.82 times 10 to the negative 10th meters along the y-axis. Okay, so this is the y-axis in bold. This is the x-axis, also in bold. So this is the origin. So if we're at 2.82 meters along the y-axis, well, 2.82 times 10 to the negative 10th meters was also the distance that separates these two, so that means 2 blocks is equal to 2.82 times 10 to the negative 10th meters. So if I'm at 2.82 times 10 to the negative 10th meters along the y-axis, that is 2 blocks above the origin, so that's right here. Okay, now before I forget, going on to the next page, you want to find the electric field at this point, when x is 2.82 times 10 to the negative 10th and when y is 2.82 times 10 to the negative 10th. This is the origin here. 2.82 is equal times 10 to the negative 10th is equal to 2 blocks. So it's 2 blocks over, 2 blocks up. So your point of interest is here. Make sure you correctly identify the point of interest, because it would be pretty sad if you went through the whole problem doing all the math correctly but for the wrong point. Okay, so this is the origin. We're 2 blocks over and 2 blocks up on page 3. Okay, so back on page 2, we want to find the electric field. We can use our equation that we have here. And I have a sodium ion and a chlorine ion. The charge from the sodium ion is the charge of 1 proton. The charge on the chlorine ion is the charge of 1 electron. If you have a single proton or a single electron, the charge is the elementary charge, which is 1.6 times 10 to the negative 19th coulombs. Okay, so that we can use E for, and E is the elementary charge given here. Now, that is the case for many of the problems in today's lab, but it is not always the case. So later on, for the last problem, when you're given 3 positive charges and they're just called Q, don't call it E, because you don't know that the charge is just from a single proton or a single electron. Okay, so just keep it as Q unless you know that Q is equal to E. Okay, I'm going to pause here and do the rest of it in a new video.